All right, 4.1. This is called the extreme value of functions. Extreme value of functions. So what we have to do is we have to unclose intervals. Unclose intervals. So what we have to do is we have to define what an absolute maximum is and what an absolute minimum is. So definitions. And then see if this mathematically makes sense to us. So absolute maximum and absolute minimum. So first we're going to let f be a function defined on some domain D. So some x part of the axis, on the x-axis, some part of this axis, this function is defined for. So it's got y values for those particular x values. Then f has an absolute maximum value, x value on D at a point C. Point x equals C is what we kind of mean about that. Because when they say point, they really mean the x value of the domain, okay? So be careful. They're not talking about an ordered pair. They're just talking about a point inside this domain. If f of x is always less than or equal to f of c for all of these x values in this domain. So really what it's saying is that when you plug in c, as opposed to when you plug in any other x value on this domain, that this function is always, the y values, the output is actually bigger than all the other outputs. So when we're talking about maximum, we're talking about, its output value. So the output at C is always bigger than all the other outputs, bigger than or equal to. So we say, and it has an absolute minimum value on D at, again, x equals C. If, well, what we're going to do is just change this on the sense of the sign. So that means every other value of x is either greater than or equal to this value of what I plug in C. So that means all of the y values are bigger than this y value if it's bigger than or equal to this y value if it's an absolute minimum for all x in this domain. So kind of pictorially, what this really would mean is, say I have a particular function, we'll do some absolute max and absolute min. And we'll see what it means by that. So if I have a function that looks like, now we're talking about functions in closed intervals, so I'm going to just say something like this. So here's our function. Now what I'd say is that this particular function has an absolute minimum at this particular value. So let's talk about D. Let's do D first. Well, D happens to be the domain of this particular function. So we're talking about the domain. We're talking about from here all the way to here. Those are the x values for which the function has y values. So this is our that is our D. These are all our x values. Now you notice how this value right here, this C value, happens to be part of the domain. And then every other x value in this thing would be considered x. So this is an x, this is a different x, this is a different x. So we leave x arbitrary for saying all the other letters where C is not. What you'll notice is when you plug this in, this happens to be f of C. But if I plug in any other x value, let's say this x value. If I plug that x value in, what I know is that its output is less than C. And not just this x value, but any x value on this red line besides that point C. So every other x value, what we can see is that every other x value, f of x, is always less than or equal to f of C. And that's why C is a maximum. So this would be, this would be considered our absolute max. Now, we notice that in this case it's an interior point, but if I take the exact same graph, I can actually say that this thing has an absolute minimum as well. So I'm going to try to reproduce that same graph. Now again, the domain here happens to be from here all the way to here. So that's our domain. It's still the domain happens to still be our x values for which the function is defined. And if I ask you its absolute min, what I'm looking for is I'm looking for the smallest value. And if you guys notice, this value is the smallest value right there. It happens to be an endpoint in this case. So what we'd say is that the absolute max is an interior point of the domain because it's inside the endpoints, and this one happens to be an endpoint. This is not an interior of the domain. This happens to be the endpoint of the domain, but it doesn't matter. This value right here, this c value right here, that c value is still part of the x values, so it's okay that it's an endpoint. But what we notice is this happens to be f of c now, right? That happens to be f of c, and if I pick any other x value, I don't know, let's say here, that x value. So if I pick any other x value, if I plot that up, what we will notice is that this guy would be f of x, just like this would be f of x. What we notice is that that f of x is always going to be greater than or equal to f of c, and that's why we have an absolute minimum at x equals c. So that's what it looks like graphically. So you could, sometimes your absolute max are interior, sometimes your absolute max are endpoints, sometimes your absolute mins are interior, sometimes your absolute mins are endpoints. It just kind of depends on the function. If I drew a different green graph, you're going to have different results. Okay, so I'm gonna define a function on a closed interval, and I'm going to see if we can identify its domain at its absolute max and absolute min. So example. What we're going to do is I'm going to give us f of x, which is equal to say x squared, and I'm going to talk about this particular function, but what I'm going to do is I'm going to change the domain, because what I'm trying to represent, what I'm trying to show here is that your absolute max and absolute min are both dependent on the function, and they're also dependent on the domain. So both of these things play a part in it. The reason why I say that is because if you look at this particular picture right here, if I would expand the domain, it looks like this function is trending down for a while. Who knows if it's going to turn back? But, if I extended the domain out, this c value would be farther over here now, because if this thing kept trending down. So it might, its absolute min might be over here as opposed to right here. Or maybe this function keeps going up and up and up and turns around, so maybe its absolute max for this function is way over here. It just depends on how much of the x-axis I decide to use. So what I'm going to do is f of x equals x squared. It's an easy thing to graph. What we know is that if I didn't give any restrictions on the domain, if I say the domain of f is going to be minus infinity to infinity, what I know is graphically this function is going to look like this. It's going to go up forever, up forever. All right. Well, let's talk about what it has for absolute maxes or absolute minimums. So, if we're trying to find an absolute max, what we're looking for is a point for which all other points are below. So it has to follow this scheme. So absolute max has to follow this scheme. So it means I have to nail down a point for which I have to nail down a c value in the x-axis, where every other x value, the output is going to be smaller. So if I try to lock down a point here, so if I lock down like this point, and I get this output right here, we can see, well, that's not big enough, because if I pick this point, that output is bigger. But if I pick this point, that output is bigger. But if I pick this point, that output is bigger. So the problem with the absolute max is there's no point that I can nail down, because this thing goes up and up and up forever. So the absolute max, you'd have to shoot all the way off into infinity in this way, or negative infinity in this way, and infinity and negative infinity is not a value. It's more of a, it's a theoretical upper bound. So it's not something I can lock down. I can't grab infinity. It's more of a concept. So what we'd say is this particular function has no absolute maximum, because it goes up and up forever. There's not a point I can nail down that I can say is the biggest. However, it does have an absolute min. Get a different color here. It does have an absolute min, and that absolute min is right. It's purple. It is. It's different than everything else. Okay, so this right here would be our absolute minimum. And the way I could kind of check that is we could pick other x values. Like if I pick this x value, you can see its output is here, right? So you have a bigger x value. Or this x value, bigger y value, I'm sorry. So every other x value that I pick besides this is going to have a y value that's bigger. So we can see at 0, so at x equals 0. So I'd say this has an absolute, wow, absolute minimum at x equals 0. And again, the reason is it doesn't need to be shown. I think it's kind of obvious, but this is because what we can see is that f of x is always going to be greater than or equal to f of 0 for all the other x's. Like if this x value is always going to have an output that's bigger. If I pick that one, this output's going to be bigger. If I pick this one, this output's going to be bigger. So 0, the output of 0 is always going to be the smallest. What now I'm going to do is I'm going to restrict the domain. I'm going to take the exact same function, but I'm going to restrict the domain of f to be the closed interval from, say, 0 to 2. So if I take the closed interval from 0 to 2, we're going to have this picture right here. Our function's just going to be this. And I'm going to put closed values here. So from 0 to 2, so 0 to 2. Now what we can see is that this actually has both an absolute maximum and an absolute minimum. What I can tell is if I pick 2, the output of 2 is going to be bigger than all the other outputs of this particular graph. So this has an absolute maximum at x equals 2. And you can tell that it has an absolute minimum at x equals 0. See if I picked a domain of f to be open at 2 and open at 0 and closed at 2. What we're going to have is we're going to have an open circle here, and then it's going to be closed right here. So what I'm trying to get down to is what happens if your endpoints are open? What happens if your endpoints are closed? Well, this has an absolute max at x equals 2. We can tell that at 2 all the other outputs are going to be smaller. But what it doesn't have is an absolute minimum. Because since it doesn't include 0, we know that this point is going to get smaller and smaller and smaller and smaller, but there's no point that I can actually nail down. Because you might say, well, what about 0.0000001? Well, I'd say there's definitely a point that's even closer to that, 0.0000001. And then what you could do is you could just add another 0 and say, well, I got one smaller. Then I can add another 0 and say that I got one smaller. We just go back and forth forever. So since we can't really nail down how close this is to 0, because what it does is it gets infinitely close to 0 without touching it. It's kind of similar how this gets infinite in height, right? So it goes on for infinity. Like the idea is you can't nail down that infinite part of it. So this has no absolute minimum. So and then D, what I was going to do is just switch these. So the domain of f is going to be closed at 0, open at 2, and for the exact same reasons, if you look at the particular graph, we're going to have closed at 0, and then we're going to have open at 2. So what we know is this is going to have no absolute max for the same reason that it has no absolute min, but it is going to have an absolute min at 0. So you can see that it's more than just a function that actually defines these absolute max and absolute mins. It's both the function and the domain. There's a lot of definitions of this particular section. It kind of builds everything that we're going to be doing for this chapter. All right, extreme value theorem. And when they give it names, they're important. So the extreme value theorem. So this says if f is continuous on a closed interval from A to B, then f attains both its absolute max and absolute min. In this interval, in the closed interval. So really what that means is there exists two values. Let's say x1 and x2 that are both in this interval, A to B, such that f of x1 is going to be equal to the maximum. So we'll call it capital M. And f of x2 is going to be equal to the minimum. Let's call it lowercase m. And another and, sorry. And that means that since this is the case, since this is the minimum and this is the maximum, that means that every other x value, the output is going to be between this maximum and minimum for all x in this close interval from A to B. Okay, so what this comes down to is the previous section, like the previous example. Notice that the only time we had both an absolute max and an absolute min is when our interval was a closed interval from A to B. So from A to B. If it was open anywhere, at least one of them was excluded. It's possible that it has none of them. You know, if you have x cubed on an open interval, from minus infinity to infinity, it has no absolute max or absolute min. So if we have a continuous function on a closed interval, you're guaranteed to have both. So kind of like just some graphs, some examples of what these things could possibly look like. So we might have something that, something that looks like this. Here's a closed interval from here to here. Now when I'm looking for the absolute max and I'm looking for the absolute min, what we can see is that this value right here would be an absolute max and this value right here would be an absolute min. Therefore, this would be that x1, which was the maximum. I just defined it to be the maximum. There's no real reason why it couldn't have been x2, but I've already defined that x1 gives us the max and x2 gives us the min. So therefore, this one happens to be x2. So that means this is f of x1, which is capital M. So this is capital M, which is f of x1. And down here is f of x2, which is going to be lowercase m. So this would be lowercase m. Now you notice that both these points were interior points, but it's, it doesn't have to be that. Like sometimes you can have sometimes it could be like this. So in this particular case, you can see that this is our absolute minimum and this is our absolute maximum. So since this is the minimum by this definition, x2 gives me the minimum, so this one would be x2. And this is the absolute maximum, so this one would be x1. So, this output would be capital M because it's the absolute max, and this output is going to be lowercase m because it's its minimum. So what we can see is that sometimes your max and mins are interior, sometimes your max and mins are endpoints. So, you can have an endpoint for maximum or an endpoint for minimum. Local or a relative extreme values. So what I mean by this is if we have a particular graph, there are possibilities that you could have a graph that kind of skirts back and forth that looks something like this. Now we're going to put it on a closed interval so I can guarantee that it attains a maximum and a minimum, but our graph could look like this. Now, what we can see is that that there are things that we can consider absolute maxes and absolute mins, but there are also points in here where one point happens to be bigger than all the other ones in its neighborhood. Now, let's look at this one for instance. Like I know that this point right here is not an absolute max because clearly this is the absolute max. But I can tell you that this point is bigger than all the other points in its neighborhood. So if I'm just looking at this part of the graph, I can tell that this is a maximum compared to those particular points. Also, this is a maximum compared to those particular points, but happens to be a maximum for all points. What's nice is that also, if you look at this endpoint right here is an absolute max for just the points that are around it. So this would be considered a, not an absolute max, but this is a max for all the points in its neighborhood. So these three would be considered relative maximums, but this one alone would be an absolute maximum. So absolute maximum is a subset of your relative maximums. Now you also have your minimums. So this we know is the absolute minimum. It's definitely the lowest. But this also happens to be a relative minimum because it's lower than all the other points that are around it. So it's lower than all the points in its neighborhood. And if you look at this endpoint happens to be a relative minimum too, because if I'm just looking at those parts of it, this happens to be smaller than all the other points next to it. So these values right here are all considered relative extreme values because the extreme values are considered both your relative minimums and your relative maximums. Now remember, even though this is an absolute minimum, this also is a relative minimum, okay? So all three are relative minimums, but this one's the only one that's an absolute minimum. So again, the absolute minimum is a subset of the relative minimums. So definitions. So, these are the extreme values. When we say that, we're actually talking about the x values for which these points are defined. Okay, so definitions. So, local maximum and local minimum. So, a function f has a local maximum value at an interior point C and its domain if f of x is less than or equal to f of c for all x values in some interval containing c. Now what this, for some interval containing c, kind of means in the neighborhood of x equals c. So what we mean by that is let's look at this point right here. Now what I'm saying is that this is a local or relative maximum because it's bigger than all the points that are kind of around it, right? So it says there just has to be some interval that contains c. So here is an interval. So let me do it in a different color. So let's just say if I'm going to take this particular interval right here. So some interval containing c, that interval right there, where let's call this one c. Can you tell that all the other x values, now any other x values, let's say this x value right here, if you plot this up, you can tell that the output of that x value is less than the output of the c value. So I can tell that every other output inside this red open interval is going to be less than the output of the c value. So what I mean by some, again, is just there exists at least one open interval. And sometimes you have to make your open interval really tiny. Like sometimes they have to be really tight, but it just has to exist some open interval where all the points are below that particular point. You know, you could have a curve that's wiggling back and forth really tightly, and all those tiny little things are going to be absolute extreme values at their crests and troughs. For a very similar explanation, a function f has a local minimum value at an interior point c, x equals c. So in its domain, if f of x is greater than or equal to f of c for all x in some, I should say open interval. Oh, I don't have open here. I apologize. It should say for some open interval, or some open interval containing x equals c. So again, this is the same idea, just in the neighborhood of x equals c. So if I'm looking at, say, a point over here, heck, I can even look at this one. I know that an absolute minimum is also a local minimum, because what I mean by local is, you know, that's why I like the neighborhood, because that's actually a math term right there. So, you know, local means in the neighborhood of this particular value. So if I'm just looking right here, an open interval, or even like really small, this tiny little open interval, I can tell all the other outputs are bigger than this output. So all the other outputs are bigger than that output at that c, at that particular c. So maybe this would be considered like C1, this might be called C2 or so on. So let's do this. This is C1, like this would be C2, this would be C3, this would be C4, this would be, and we'll talk about the inputs in a minute. The reason why this has to be excluded from the endpoints is because we're talking about an open interval that contains C. So you have to have a little bit below and a little bit above. So at the endpoints, you don't have that exact same open interval. What you have to do is you have to do kind of like a half interval, I guess I'd say. So this side would be open and you have to include this. But yeah. Okay, so all right, let's continue. All right. Maybe I should leave this up for a quick second. So what do we notice? what I notice is that some of these what I'm trying to do is I'm trying to get to testing this. Well, okay, let's just kind of go off the cuff. So what do we kind of notice here? Well, sometimes your maxes and mins. So sometimes we can see the local max / minimums are at the endpoints. I shouldn't say sometimes, always. Your endpoints are always going to be a local maximum or minimum. I'm going to turn that down. It keeps getting us. So these are always going to be considered a local maximum or a local minimum. You just have to figure out if it's going to be below or above. You know, is the graph trending down or is the graph trending up if it's a right endpoint or a left endpoint, respectively. So, or vice versa. So, I shouldn't say sometimes local maximum. That's always. So not always, but always local max and mins are at endpoints, always. So that's always going to be the case. The other thing that I notice is if we're looking at these local maximum and minimums, since they're happening at like the cusp or the trough of these things, do you notice something about the tangent line? So if I was going to look at the tangent lines of these particular things, what do you notice about the slope of the tangent line there? What do you notice about the slope of the tangent line there, and here, and here? Well, what we notice is that the slope of those things are going to be equal to 0. So we notice that they have horizontal tangent lines. So at your interior points, the local max and mins have horizontal tangent lines. So this kind of gives us a way of testing these things. So how do we find these things? Well, we know that these are always going to be local maxes and mins, so how do we find the other ones? So this is called first derivative test. For local extreme values. So what that means is if f has a local max or local minimum value at an interior point, x equals c of its domain, and f prime is defined at x equals c, then what we know is that f prime of c has to be equal to 0. What we notice is that your local maximum minimums for interior points will always have horizontal tangent lines. What that means is that the derivatives are all going to be equal to 0 there because the slopes are all 0. The slopes of the tangent lines are all 0. Now we have to be a little careful. Does this guarantee if the derivative is equal to 0, then do we have a local max or min? So let me come up with a picture that we have to just kind of verify that if that's the case or not. So here's a quick example just to kind of see. How long are we going to go on for? So let's do a closed interval. So I'm going to start at here. Let's start here. Closed interval. Boom. So I'm going to come up here, drop it out. So there's a graph of bars, and what I've done is I've done a continuous function on a closed interval. So what I know is that the extreme value theorem tells us that if it's a continuous function on a closed interval, it's guaranteed to obtain an absolute max and absolute min. But right now we're really only caring about local maxes and local mins. So what I can see is that that we have locals, of course, at the endpoints, because they're always local max and mins, but we also have one right here, and we also have one right here. That's a local max, and that's a local min. Now, if I know that the derivative is going to be equal to 0 here, so this is going to have a horizontal tangent line here. So in this case, at C1, I know that f prime of C1 is definitely going to be equal to 0 because the slope of that purple line is 0. I also know, I'm going to call this one C3, and you'll see in a second that C3, that f prime of C3 is also going to be equal to 0. So f prime of C3 is also going to be equal to 0 because the slope of its tangent line is equal to 0. But do you notice there's another point right here? Now, it didn't have to go through the origin. I just, it helped me flatten it out is the only reason why I did it. So, you know, this graph could be shifted up a couple units. But notice right here that this thing has a horizontal tangent line. And what I'm using is I'm kind of using the idea of like x cubed. If you look at x cubed, it flattens out at the origin and it goes back up. This also, this C3 right here, the C2 I mean, f prime of C2 also happens to be equal to 0. But is that a max or a local max or a local min? It's not, because up here, remember when we're talking about a local max or a local min, I'm going to grab some open interval. So here we go, open interval. Now, for it to be a local maximum, that means every other point has to be below that purple point. So what if I pick up this x value here? We can see the outputs right there are going to be bigger than the outputs here. Well, then maybe it's a local minimum. So that means all the other outputs have to be bigger. Well, over here they're bigger, but over here they're smaller, so it's not. So it just doesn't follow that scheme. So what this means is, if we're going back to this idea, it says if it's a local maximum. So what we mean by that, if it's a local extreme value. So what that means is local maximums or mins. This definitely says that the derivative of these c sub k's are going to be equal to 0. C sub k, because there's possibly a bunch of them. But it's not guaranteed to go the other way. It only goes in this one direction. If it's a local extreme value, its derivative is definitely 0. Now we're talking about interiors, okay? So interior. So notice that these are local extreme values. They're in the interior. Their derivative is equal to 0. But just because their derivative is equal to 0 doesn't mean they're a local extreme value. So really, when we're going to start solving for these, what we're going to be doing is we're just going to be looking at candidates. So these are going to give you, again, we're going to use this to our advantage to be able to find our interior local maxes and mins, but we're not going to, it's not going to definitely give it to us. We're going to have to verify that it is still the case. That they are indeed extreme values. Okay, so example. To do an example yet? Not yet. Not yet. We're almost there, I promise. Okay, so definition of a critical point. So this is going to be called a critical point. So an interior point of the domain of a function f, where f prime is 0 or f prime is undefined, is a critical point. So just note these critical points are possible extreme values. Remember, they're only possible, okay? So the reason why we also say undefined is because, you know, you could have a graph that looks like this. So we know that that it could look like this, but it could also have a sharp point. And what we know is that the derivative is not defined there, and that actually would be a local maximum. So that's why we have to worry about when it's 0 and when it's undefined. So when it's 0 because of this one over here, and when it's undefined because of this one right here. And we should have said closed interval because that's what we're studying in this particular section. So clearly those endpoints are extreme values, that being a max and that being a minimum. And what's funny is I did a horizontal tangent line by accident. That's also a critical value. So critical value, critical value, critical value, but only those two are interior extreme values. That one is not. Okay, so how to find? Absolute extrema of a continuous function on a closed interval. Now, extrema is a shorthand way of this says absolute max and min, so that's what they mean by extrema. So just another way of saying both words at the same time. Your extreme values. All right, so one, determine all critical values. So what we're going to do is we're going to solve f prime of x is equal to 0, and f prime of x is undefined. And these x values, what it's going to give you is x values are going to give you your c sub k's. You're going to get c values from these. You're going to get values, and these are going to be our critical values. 2, we're going to determine the endpoints. Well, the endpoints are going to be given because they're going to give us our interval. They're going to say f of x on this closed interval, so they're going to tell us what the endpoints are. 3, we're going to evaluate all. We're going to evaluate the critical values and the endpoints on f. So we're going to plug them into f. You're going to take all these values and all these values, you're going to plug them into f. The largest output is the absolute max, and the smallest output is the absolute is the absolute min. All right, let's make this happen. So that's what we're going to do, finding critical points. So, example. Find the absolute max, oh, I'm capitalizing it, absolute maximum and absolute, I might as well capitalize this one as well, absolute minimum values of the function on the given interval. Okay, so we're going to go through the test that we did here. So our very first one, f of x is going to be 4 minus x squared, and our interval is going to be minus 3 less than or equal to x less than or equal to 1. Now sometimes they give it to you that way, and sometimes they write it this way, okay? They both mean the same thing. So that's our function, that's our closed interval. All right. So step one, critical points. So what I need to do is I need to go f prime of x is equal to 0. So I have to take the derivative of this and plug it into here. Well, the derivative of this is going to be, the derivative of 4 is 0, the derivative of this is minus 2x is equal to 0. So what I get is I get, divided by negative 2, I get x is equal to 0. Second, we need the endpoints. Well, my endpoints are x equals negative 3 and x is equal to 1. So there's my candidates. I have 1, 2, 3 candidates. So the third step I'm going to do is I'm going to take those numbers and I'm going to plug it into f. So what is f of 0? I want to know what is f of negative 3, and I also need to know what is f of 1. So make sure these are going back into the original function because we need to know its outputs. So for this one, it's going to be 4 minus 0 squared, so this gives us 4. This one is going to be 4 minus negative 3 squared, so 4 minus 9 is going to be negative 5. And this is going to be 4 minus 1 squared, so 4 minus 1, which is equal to 3. So of these values, what one's the absolute max and what one's the absolute minimum? So we'd say is the absolute max, I love capitalizing that for some reason, absolute max is x equals, I apologize, the absolute max is 4 at x equals 0, and the absolute minimum is negative 5 at x equals negative 3. So those are the values of their max and min respectively, because when we talk about being biggest and being smallest, we're talking about outputs, but they happen at those particular endpoints. So, you know, another way you could say is, you know, this is at 0, 4, and this is at minus 3, negative 5. What's nice is if you, I'll do a little picture over here just to kind of show you what happened. So what I know is that this is 4 minus x squared, so this is a parabola, it opens down. It goes from minus 3 to 1. So graphically, it's going to look like, and this one all the way down. So graphically it looked like this. It was closed interval here, and this happened to be equal to 3. So this is what it looked like. It was that closed interval. And we can see that this is your, you know, this point was your absolute min. This point right here was your absolute max. And that's how we got those. All right. That's a little broke. That's okay. I got this. So, it's got to be pi over 4. Okay. So, B. F of x is equal to, say, the cosine of x. And on the interval from pi over 4 less than or equal to x, less than or equal to 3 pi over 4. Let me make sure. Oh, minus pi over 4. All right. So, step 1. We have to do f prime of x is equal to 0. So the derivative of the cosine of x is minus the sine of x is equal to 0. Now remember that we are restricted to this domain, so minus pi over 4 to 3 pi over 4. closed interval. So if we go to our unit circle, we know that we were restricted from there to there. So I'm going to show you this. What I know is I'm going to go from minus pi over 4, which is right here. I guess I can do it in red. So minus pi over 4 all the way to 3 pi over 4. So we're talking about just those values right here. So that's going to be our restriction. So what I want to know is, when is the sine of x equal to 0? Well, I know it's just the sine of x, but if I have minus sine of x is equal to 0, I can multiply both sides by -1, so it still gives you the sine of x equal to -1 times 0 is 0. So this is when the sine of x is equal to 0. So remember that the sine of x happens to be the y coordinates. So what I'm looking for is I'm looking for 0 in the y coordinates. And what I can see is that the sine is equal to 0 right here. So the sine is equal to 0 here, so that means I have 0 radians. So this gives us a 0. So that means x is equal to 0. Now, the second one, I have to look at our endpoints. So the endpoints are going to be x is equal to minus pi over 4 and x is equal to 3 pi over 4. So these are my candidates. Again, I got 3 candidates, and we're going to plug those back into the original function for cosine. So 3. I'm going to check, I have to evaluate it, so let's see how I did that to make it look the same. So 3, I'm going to plug it back in. So what is the cosine of 0? What is the cosine of minus pi over 4? And what is the cosine of 3 pi over 4? So make sure when we go back to our unit circle that the cosine are your x coordinates. So at minus pi over 4, which is the same thing as 7 pi over 4, your cosine is root 2 over 2. So this is root 2 over 2. And that's wrong, I apologize. That's this one, minus pi over 4 is root 2 over 2. The cosine of 0 is 1. And then the cosine of 3 pi over 4, which is over here, happens to be negative root 2 over 2. So this is minus root 2 over 2. So, what one's the biggest, what one's the smallest? Well, you can tell that 1 is bigger than this, right? Root 2 is about 1.41 divided by 2 is going to be smaller than 1. So 1 is bigger than that other positive number. And since this is negative, it's clearly the smallest. So it means I have an absolute max of 1 at x equals 0. So another way to say that is 0, 1 is our absolute maximum. And I have an absolute minimum of negative root 2 over 2 at x is equal to 3 pi over 4. Or this is the point 3 pi over 4, minus root 2 over 2. If we look at the graph, if I wanted to look at the graph of the cosine function, we're going to go from minus pi over 4, 0, pi over 4, pi over 2, pi, what are the other ones? I'm just going to go by that. So pi over 4, pi over 2, and then eventually 3 pi over 4, pi over 4, pi over 2, and then it's going to be 3 pi over 4. So it looks like this. So every 45 degrees. So what I know is that negative pi over 4, that endpoint at negative pi over 4 was root 2 over 2. This is equal to 1. So here, and then we went down to process here. Goes down to negative root 2 over 2. So you can see is that the cosine function looks like that. So you can see that absolute maximum. So at 0, 1 is our absolute maximum, and at 3 pi over 4, minus root 2 over 2, that's our absolute minimum. All right. C. f of x is equal to 1 divided by the square root of 1 minus x squared. I'm trying to give you guys a little bit of, like, one of everything. I gave you something that's polynomial, something that's trigonometric, and then this is also radical / rational at the same time. So, well, it's not rational, but it's radical in fraction form. All right, so what I know, am I even given a closed interval? Yes, it definitely is on a closed interval. I'm not actually going to define that. We're going to have to talk about this. So I'm just giving you this function, but I have not defined a closed interval. So we'll have to kind of determine what that particular closed interval is. So, a quick question. What is the domain of f of x? Back to pre-calc, what we know is, before I can do anything, I'm going to have to find this domain. Well, what we know in pre-calc is, first thing, 1 minus x squared is not allowed to be 0 because it's in the bottom. So if I solve this, I know that 1 minus x squared is not allowed to be 0 if I square both sides. And since this is in standard form, there's no x, I could just solve for x and then square root it. So 1 is not allowed to be equal to x squared, square root it, plus or minus. The square root of 1 is not allowed to be x. So that means x is not allowed to be plus or minus 1. The other thing I have to worry about is I know that 1 minus x squared has to be greater than or equal to 0. The reason why is you can't square root negative numbers, so you have both of these to consider. So minus x squared is greater than or equal to -1. When I divide by a negative sign, you're going to switch the sense of the sign. Actually, the easiest way to probably pull this off, I don't like what I'm doing here. I'm gonna do this graphically. What you're going to get is this isn't going to work. What I know is that 1 minus x squared, that particular picture, is going to be a parabola that opens down, shifted up 1. So if I'm going to look at negative x squared plus 1, so I know that it looks like this. So it opens down. It would look like that, right? Remember, that's just the radicand. That's just this part of it, okay? Because I want to know when it's greater than or equal to 0. So we can see that it's going to be greater than or equal to 0, this part of it, right? Here is where it's positive. And then if you want to find the zeros, we already have. This happens to be -1, this happens to be +1. So what that means is that this thing is greater than or equal to 0. The solution to this particular expression is going to be from -1 to 1. Now, you have to take the intersection of these two particular domains. So what I know is that the only way for this to work at the same time is we have to be in between -1 and 1, so we have to be here, but I'm not allowed to be those particular -1 and 1. So what we're going to get when we're done here is just going to be the open interval from -1 to 1. So from -1 to 1. That's going to be the domain of this particular function. So unfortunately, I cannot guarantee this has an absolute max or an absolute minimum, because it's a continuous function, but not on a closed interval. It's actually on an open interval. All right, so let's just go through the work though. So really, what this is this domain is -1 less than x less than 1. All right, so let's just see what happens then. So number 1, f prime of x is equal to 0 or undefined. So we have to figure out when this is. So other reason why I know that I'm going to include the undefined is because I have a fraction here and I have square roots. So things I just have to be careful of. The other particular functions were they're never undefined because they're smooth continuous curves.